So we're going to move on to the next two type of calculations that we might need to do in time of flight. So we're going to calculate the length and then the time of flight. So the length is the distance in that separation region that the ions travel while they're being separated by their mass. So we need to remind ourselves that kinetic energy is a half mv squared, but that the v part is where we're going to get the length, the distance, from v is distance divided by time. Velocity is distance divided by time. So here's our example question. We've got our ion, it travels through the flight tube with an energy, that's our kinetic energy. So this is our kinetic energy. This isn't directly, we're going to use it, it's not directly our mass, we're going to calculate m from this. And we've got our time t here. So if we're not sure in an exam, one of the things we could do is do something we've practiced already, and that's calculate the mass. So can you pause the video, use your calculator to find the mass of one strontium ion? So if you've remembered that calculation correctly, you should have got that, 1.428 times 10 to the minus 25 kilograms as your mass. Okay, we've got the kinetic energy now, and we've got the t, and we need the distance, the length. Now to get the distance, we're going to need the velocity and the time, but we haven't got the velocity, we've got the kinetic energy. So again, using the calculation that we've already covered in the previous video, could you work out the velocity? So can you remember how to work out the velocity of an ion? Pause the video again and have a go. So if you remembered that calculation correctly, you should have got 164021 meters per second. Now we can put that with our time. If velocity is distance divided by time, then distance is velocity times time. So take that velocity and times it by the time given to you and see if you can work out the distance in meters. And if you've done that correctly, you should get 1.79 meters. So that's how we'd calculate the flight path, the length of the flight path, or the time, the distance that the ions have had to pass in our mass spectrometer. So that's that middle separation section. How big is that middle separation section? Now think about the size of the machine and think about what could be realistic. So if in the exam you get an answer here that's 0.00001 meters, think about that. Could your machine be the size of the head of a pin? Is that possible? Or if you get an answer that's thousands of meters, how would you fit that machine into a room? So what is a likely answer? So you're probably looking for answers between maybe half a metre and probably not much more than 3 meters. Think about the size of the room. You're not looking for very big or very small answers here. Okay, our final type of calculation is probably one that is the most tricky, but there is a little shortcut and if you can get your head around this shortcut, it'll make your life easier. So the sort of calculation we're looking at here is if you know the time of flight of one ion with its mass, so I know that the magnesium 24 ion takes 1 times 10 to the minus 5 seconds, then I can work out how long the magnesium 25 ion will take with quite a simple calculation. But why it's simple is where the trick comes in. So what we need to remember is that all ions with the same charge are given the same kinetic energy. So as long as they've all got a 1+ charge, which is what we hope for in our mass spectrometer, they will all have the same kinetic energy. And since that expression is kinetic energy is a half mv squared, and v velocity is distance over time, we could rewrite the kinetic energy expression as kinetic energy is a half m, and then v squared becomes d over t squared. Okay, and if you want to expand that bracket, then you could say that's the same as a half m d squared over t squared. Now given that we know that the two ions have exactly the same kinetic energy, if we have ion 1 and we say that ion 1 is going to have mass 1, the distance in the machine is the same for both ions, but the time is different because the heavier ones move slower. So we've got T1 and M1, they're the things that are different for the two ions, but the two kinetic energies are the same. So we've got still the distance the same, but the times and the masses are different. We've got this expression. Now there are some things that are the same on both sides, so there's a half on both sides, so we can cancel it. There's a d squared on both sides, so we can cancel that. We can't cancel the masses and the times because they're different masses, so we get m1 over t1 squared equals m2 over t2 squared. And then there's another little trick. You could, if you wanted to, convert those masses into kilograms, which you should do for nearly everything in time of flight mass spectrometry. But what you'll find is, if you think about it, if to convert to kilograms, you would have done mass 1 times 10 to the minus 3 divided by Avogadro's, and that would be our new mass value, and then we'd divide that by T1 squared. And we do that to mass 2 as well, times 10 to the minus 3, divide it by Avogadro's, squeeze that in, divide by T2 squared. What you can see is that the Avogadro's bit's cancelled and the conversion bit cancels. So you could just bang in the isotopic masses and you will get the right answer. Right? So in this calculation, you can just use relative isotopic mass. So let's have a look at how that would work. This is our M1, and this is our T1, and this is our M2. So m1 over t1 squared equals m2 over t2 squared. So m1, 79 over t1 squared, 2.055 times 10 to the minus 5 squared equals m2, 81 over t2 squared. And we've got to find t2. Now, if you struggle with algebraic rearrangements, my suggestion would be to calculate the value of the left-hand side of this expression to work it out. If you're confident with your rearrangements and you feel happy with the algebraic rearrangement, then you should be able to rearrange this and get a value for t2 squared initially. So if I were to show you that, if I move t2 squared up to the other side, it will come up to the top. I'll multiply both sides by t2 squared and then divide both sides by 79 and then times both sides by t1 squared. Or because I've got two fractions, if you remember from school, from your GCSE maths, you could flip this fraction upside down. Because you've got two fractions, you could flip them both and it would still be correct. What you're going to find is that t2 squared is 81 over 79 times by that mass. Now, if you find the algebra rearrangement difficult, calculate the number on the left-hand side and then do the algebra. It minimises the amount. See if you can work out what t2 squared is, and then see if you can work out what t2 is. It should be similar to t1, because they are similar in mass, so they're not going to travel that different speeds. So just think about your numbers. And if you've managed that, you should have got 2.08 times 10 to the minus 5 seconds. So that's our calculation section to do with time of flight mass spectrometry finished.